Good morning, everyone. My name is Masoud Mansoury. I'm from Delft University of Technology. For this talk, I'm very happy to present the basics of the recommender system. So I will start with a brief introduction about the recommender systems, the basic pipeline, the forms of the input and output for recommender systems, and then I mainly focus on the recommendation models, with traditional recommendation models to widely used models, collaborative filtering, and content-based recommender, then a hybrid recommender system combining multiple recommender systems, recommendation models, and then I will talk about some advanced recommender models, like context-aware recommender, calibrated recommendations, and the advances of the item-based neighborhood model. Certain algorithms developed to tackle the limitations of the item-based neighborhood models. And if you have time, I will also briefly talk about the evaluation. So recommender systems are perceived as a subclass of the information filtering. These systems are decision aiding tool helping users to find their preferred items. So it's helping for alleviating the problem of the information overload, which we are encountering in any platform, online businesses that we work with in our daily basis. There are many different examples of such a system. I mean, commercial systems, or maybe systems developed in the academia, group lens, or I mean, movie lens developed by the group lens group is the movie recommendation system is developed for the process of the research. Recommender system in Amazon, the product recommendation, the domain for each of these platforms might be different. So here in Amazon is product recommendation. Movie recommendation in Netflix, that based on the behavior and the interaction that the user have with the movies, it generates the recommendation. So also there is also, I mean, an important event related to this company for the Rexis community in 2008 or 10. If I remember, there was a competition organized by Netflix, which helped a lot for improving the research in recommender systems. Google News, which is basically, I mean, mostly based on maybe content or maybe the implicit behavior feedback of the users, recommending news to the users, and friend recommendation in Facebook, which might be considered different than the other ones I showed you in previous slides. In the previous ones, we had items to be recommended to the users, but here the recommendable item is also human. So human is recommended to the human. So it has different properties. Also, it is known as link prediction in social network analysis. So the basic problem in recommender system is estimating a utility function that automatically predicts the preferences of the users, the item that the user might like. Based on the user's interaction with the system, it forms the input for the system. So the input, the interaction of the users would be in various forms, like click, rating, or maybe browsing of the platform. So the recommender system takes these input data, processes them, and then learn the user preferences and the item characteristics. And based on these preferences and characteristics for the users and items are in the form of the embedding or latent factors. So matching them would help to recognize which item would be preferred by the user to be shown to the users. This slide shows the basic pipeline, very basic pipeline for the recommender system. Given the input, we have a recommendation model, we have the output. So I will briefly show you basic forms of the input data output for the recommender system, the ones that are used in the literature, mostly in the literature, and mainly I would focus on the recommendation models. So regarding the input data, we have like in very simple setting, we have user items. Items also are associated with certain metadata, maybe content information, as you can see in the right. So users make connection or maybe interact with the items in the system. So these interactions are collected by the system, and then they are used for building the recommendation model. So depending on which recommendation model we are using, certain types of input data would be used. So in the following, you would see different types of the recommendation model, and each model would require certain types of the data for the processing. So the right part here, you see the content information. The left part, you see the interaction data. Interaction data here, it looks more like a graph data, but it can be in different forms. Of course, graph can be also an input for the recommendation model if the model can process it. But sometimes we have the structured data, stored in the form that you see in the table in the left. And for some models also, we need to transform these structured data or graph data into metrics in order to be processed by the recommendation model. So these are different forms of the input data we have for building a recommendation model. So here in these metrics, we have users in the rows and items in the columns, and entries are the ratings. Question marks are the missing values, the values that we need to, the entries that we need to predict. Our recommendation model is going to predict. And regarding the recommendation output, again, we have various forms of the recommendation outputs. Two major ones are rating prediction, that we build a recommendation model to predict the rating value for missing entries in our metrics, as you saw in previous slide. So it is also known as the metrics completion problem. The second one is ranked list, which is also maybe more popular in the research community. So the ranked list refers to the fact that we build a recommendation model. We do not, it doesn't matter what the rating for a target user on a target item would be. Here, we only predict the score, and then we rank the predicted score for each item, and then we return the ranked list for the target user. This task is also known as top K recommendation problem. So here I have an example for both tasks. For the first one, the input for both tasks are the same. We assume the input is the same, recommendation model is the same, but the output might be different depending on the task at hand. So in the rating prediction, we try the red entries here are the predicted rating values, but the second task is the ranking task that so we do not predict the rating, but we just predict the relevance score for a target or unseen items for a user, and just rank the unseen items based on the predicted score. And then we return K items as the recommendation list for the user. So these are the forms of the output. Regarding the recommendation model, so far we just briefly talked about the recommendation input, the recommendation output, the basic forms of the input and output. Now we talk about the recommendation models. So the first model or the approach is collaborative filtering. So in this category, we have also two other subcategories for this approach: neighborhood models and model-based recommendation approaches. So collaborative filtering refers to the approach that we only use the interaction data collected from the user behavior, user interaction with the system. So It can be in the form of the click data or maybe rating data or any other form that the user interact with the system. It uses the wisdom of the crowd, the opinions of the other users for building the recommendation model, also recommending items to the users. So one group of the algorithms on collaborative filtering are neighborhood models. There are two forms of algorithms in this category. We have user-based neighborhood models or user-based collaborative filtering and item-based collaborative filtering. So in user-based collaborative filtering, we leverage the opinions of the neighbor users to a target user to predict the rating or maybe generate the recommendations for the target user. So the task here would be first finding the similar users to the target user. Those similar users are also called neighbor users. And then based on the opinions of the similar users or the neighbors, we take their opinions to predict the rating for the target user on target item. But on the other hand, for the item-based neighborhood model, we compute the similarity value instead of between users, we compute the similarity values between the items. So we have a target user with a history of the interactions item that user interacted. We compute the similarity between all the unseen items with the interacted items by the user. And then based on the similarity value, we recommend the most similar items to the target user. I have some examples, maybe it's easier to explain. So in the user base, in this example, you assume that we have 3 users and 6 items in the system. And also we have the interaction between the users and items. Our target user here is John, for example, and we just want to know what would be the best candidate items to be shown, to be recommended to John. So here, if we go for the user-based neighborhood model, we first need to find the similar users to John. Based on the interactions, we see that Tim is the most similar user to John because both items that John interacted or liked in the past, I mean, this one and this one, we see that Tim also interacted with both. So this means that Tim is the most similar user to John. And then based on this similarity pattern, we can see that there are 2 other items that Tim liked, but John has not interacted yet. So this means that probably because Tim is similar to John, those 2 items, unseen items by John, would be a good candidate to be shown to John. But on the other hand, for item-based, we have the same example, John as the target user. We just want to see which item would item-based recommender model would recommend. So here we go for the item similarity among the items, all the items that John interacted in the past. John interacted with 2 items, this one and this one. This one doesn't have any similar item because there is no overlapped rating between this item and other items in the system. But this one is the item that John liked and 2 other users also liked. And we are looking for the other items that John hasn't interacted yet, but the 2 other users liked. So there is one item here, this one, that Amy and Tim both liked in the past. So we see that this item consumed by John and some other users, there is another item that those other users liked, but John has not interacted yet. So probably we can say this is first item here is the best candidate to be recommended to, yeah, so this one is probably the best candidate to be shown to John. So these So this is the example of the basic mechanism behind item-based and user-based collaborative filtering. Now we'll go to the formulation of these algorithms. So user-based, also the same formulation for item-based. Some first questions for these algorithms are how to measure the similarity between the users or between the items. Then after we computed the similarity between the users and items, how many neighbors or which neighbors we should select to use their opinion or their rating for predicting the rating. And the last one is, okay, you have the neighbors, how do you predict the rating or how do you generate the recommendations? Let's answer this question. So here we have this, for example, this is small interaction data, this matrix. And these are the notations I'll try to explain in the equations. So the first step is similarity computation. We have different similarity functions, Pearson correlation, cosine similarity, Jaccard coefficient. So it's maybe it can be like a hyperparameter. You try different similarity function and chose the best like results in the best performance for your specific data set that you're working on. But here for user base, I will show you one of them, Pearson correlation, and for item base, I will show you another similarity function, but there are more that you can explore. So Pearson correlation follows this equation, which is so in the denominator you have basically the dot product of the rating between the target user provided to the target item and the neighbor users, just to see how similar these two users, their rating patterns are similar. And the denominator is simply the normalization factor, just to make the value from Pearson correlation to be in the range of 0 and 1. So example computation here for two users, user U1 and user U3, based on their rating patterns. First, we compute the average rating for each user. Then we find the overlapped items. So here, this overlapped items is very important because sometimes it's sometimes hard to find the commonly rated items between the users if the data is highly sparse. So that's why sometimes these algorithms do not work well, which we will also talk about the limitations of these algorithms later. So these are the sets of the overlapped items, the items that both users rated in the past. And then we compute the deviation part in the equation, and then by putting the numbers in the equation, we have the similarity value between these two users. As you can see, it's 0.944, which is like a high similarity value between them. And for the rest of the users, we do the same. We compute the similarity value between target user, which in our case, it is user U3, and all other users in the system. So this table here shows the similarity value between U3 and all other users in the system. The second step is neighbor selection. So we just computed the similarity value between all the users in previous step. Maybe we have millions of the users. It's like it's a big company, or maybe you have large data set. So which neighbors we should use? We should select for the next step. So one way, which is also best practice, also we use in our work, is that we select k users among all the neighbors or the similar users we computed in previous step. The value for k is of course a hyperparameter. We tune it experimentally. We tune the value for k and select the best value, and we use those k neighbors as the neighbor for the target user, and also we use their opinion for predicting the rating. The last step is rating prediction. We have the similarity value. We have the similar users. We have the degree of or maybe similarity value between the neighbors and the target user, and now we need to compute the rating. or if it's a ranking task, we need to compute the relevance score to rank the unseen items and show them to the users. So in this equation, the first element is the average rating for target user, the average rating of the target user. This bigger term is the weighted average of the rating provided by the neighbors, by the similar users. So we just take the weighted average of the opinions of the similar users. And specifically this term, so this term here, this deviation, the subtract of the rating by the mean of the neighbor user, we use this one to avoid, to just capture the differences in the behavior of the users in providing rating to the system. So here you have, I'm showing you two examples, user A with this rating pattern and this user B with this rating pattern. So as you can see, so this user, first user, user A is a user who tends to rate high. B is a user tends to rate low. So yeah, these are two different users, but the meaning of their rating might be different. So here for user A, 3 might mean low rating, but for user B, it might mean high rating. So just to capture these differences, we have this term in the rating prediction equation just to compute the mean center, the difference of the rating with the mean, just to capture the differences of the users in providing their rating to the system. So given this equation, rating prediction equation, also the similarity values we have for the neighbor users. For the example, if we want to predict the rating for this question mark for item I6 for user U3, we first, and also assuming that K is 2, we just want to work with 2 neighbors. What we do is that we just take the similarity values between user U3 and the 2 neighbors, and the rating that the neighbors provided on item I6. Then we just compute the weighted average across the opinions of the neighbors on the target item on I6. As you can see, the similarity value is multiplied by the rating of each neighbor on I6, our target item, the same also for the second neighbor, and then we normalize it, and the predicted rating would be computed. So it's 0.86. We also did the same process for another item, for item I1. The predicted rating is 3.35, and then we can say between these two items, we can say item I1 might be more preferable for target user, for user U3. So this was user-based collaborative filtering. Item-based collaborative filtering follows the same logic, but instead of computing the similarity value between the users, we compute the similarity value between items. So again, we have the same metrics, but here we look for the similarity. We just look at it column-wise. In the previous one, we looked at metrics, row-wise, but here we are looking for the similarity between the vectors of the ratings for items. So we look at the vector or the profile of the items instead of users. So the first step would be similarity computation. Here for this one, I'm showing you the cosine similarity, another similarity function that we compute, same process. We just compute the similarity value between the rating patterns in 2 vectors. For example, item 1, item 2, 2 items. And also it is normalized also to, the range to be between 0 and 1. And for the similarity computation, as an example for item I2 and I6, we first extract the overlapped users who rated both items. And then we put it in the equation, and then we just compute the similarity value. We do the same process for all other items in the system between item I2, which is our target item, the item that we just want to see what rating would be predicted, would be given to this item by a target user. So first we need to compute the similarity value between this item and all other items. And the second step, again, we need to select the neighbors. We follow the same process, k neighbors, which experimentally tune this value for k to find the best number of the neighbors for the target item, and then we predict the rating for the target item by target user. So the example here is, for example, if we want to predict the rating value for this item I2 on by user U5, we first need to determine the number of neighbors, assuming we set the number of neighbors as 2, so we pick the most similar items, 2 most similar items to the target item, which are item 1 and item 3, these two. And then we use the similarity value between target item and those neighbors and the ratings provided by the neighbors, similar items by the target user. So we have target user as U5, the neighbors are I1 and I3, these two ratings, 1, 2 ones here we have, and the similarity value between item I2 and the item I1 and I3, the two neighbors for this target item, and then we compute the rating for this item by user U5. So this was the item-based collaborative filtering. They are more, basically similar, but the processing, the similarity computation is a bit different. But comparing these two models, based on the research so far, it has been shown that item-based is able to recommend more relevant or is more effective in generating the recommendation list. We can just see this from the processing, from the mechanism behind each algorithm. So in the item-based collaborative filtering, we recommend the items based on the history of the interaction provided by the user, by the target user. But in the user-based, we follow the opinions of the other users. So for example, if, for example, similar items to a target historical movie, if you want to, for example, find, if you have a user interested in historical movies, in item-based collaborative filtering, there is a higher chance we also recommend historical movies. But in the user-based collaborative filtering, because we're using the opinions of the other users, there is also chance we recommend something else, not exactly the same pattern, same interest that user like in the past. But on the other hand, user-based collaborative filtering is also effective in terms of diversity. So also in the previous example, as I said, item-based collaborative filtering tends to follow the preferences of the user. If the user likes certain genres or maybe items in the past, the recommendations would also contain the same genres or maybe same content recommended to the user. But in user-based, because you follow the opinions of the other users, there is also chance to recommend something beyond the interest of the users. So that's why we say user-based collaborative filtering might be more effective in terms of diversity, recommending more diverse items to the users. And item-based collaborative filtering is known to be more transparent, it's easier to explain why a certain item Yeah, for the user, it might be more clear why certain items are shown to the user. So in terms of explanation, we can say maybe this item-based collaborative filtering might be more preferred than user-based collaborative filtering. And in terms of the weaknesses, while these two approaches, these two algorithms are operating, I mean, simply by doing simple computations, but their offline, the training phase for these models is a challenge, because we will see also in the next slide the limitations, also the following algorithms that try to improve these models. But the offline part requires a lot of computation and resources. And the important limitation of these models is the sparsity issue or cold start issue among the users and items. If we cannot find the overlap between, for example, computing the similarity between two users, if the two users do not have overlapped items, then the similarity value cannot be computed. If they have few overlapped items, then the similarity value, even we compute, then the similarity value would not be that accurate. So the sparsity is the main, major limitations of these algorithms. Regarding the strengths, easy to implement, might not be that, maybe in these days might not be the strengths, but these algorithms are simple and also, easy to justify, to explain the recommendations. They do not follow complicated process that you cannot understand why certain items or recommendations are generated. And also with the new items or new ratings, added to the system, first, the model can be easily updated. It's not the case for other complicated models. And also it doesn't change the prediction, the recommendation results when few new instances are added to the data. So these were about the user-based and item-based. I'm not sure, can we have the questions now, or we should leave the question at the end, Q&A? Yeah, so if you have any questions so far, let me know about these two algorithms. Yeah.
Thanks, question about any good slide number 23.
Yeah.
Yeah, actually, I want to ask you, why do we need to select similar users, but we do not pay attention to the users that are very different from this specific user? Because, for example, here, user 3 and 4, I think they have opposite ideas about almost everything. So why we do not use this signal?
Yeah, good question. This is also maybe the idea maybe developed after these original algorithms are developed, that people said, okay, opinions also matter. I agree, you're right. So here I just try to show you a basic example about the original algorithm, how it was developed, but incorporating the negative opinions also helps to improve. In the following slides, for the improved algorithms, the algorithms that try to improve item-based or maybe user-based neighborhood models, you will see the objective function, the learning process is changed to take into account the negative opinions in order to improve the algorithms. Yeah, but we can consider that, maybe we can, for example, take the neighbors with the absolute value of the similarity values. Then maybe you're right. This user, I think 4 would be selected as one of the neighbors. Yeah. Any other questions? Okay. So these were the neighborhood models under collaborative filtering. We have another sets of models under collaborative filtering. The neighborhood models are called memory-based approaches. they follow the k-nearest neighbor, the KNN approach in machine learning for predicting the rating. The second category is model-based methods, or what we call matrix factorization as the, widely used algorithm in this category. So this in this approach, we identify the latent factors for the items for the users that explain the patterns in the data, the characteristics of the users and items. So here you see an example given the input data. For example, M users, N items, the metrics that we saw in previous slides. This model learns two low-rank matrices, P and Q. So P would indicate the representation or characteristics of the users with D factors. So fact D is a hyperparameter we specified. But the factors for a specific user here, the factors, the vector, which is kind of embedding for the user, represents the characteristics of the user. We have the same also for the items. So for each item, this vector or the embedding represents the characteristics of the items. For predicting the rating for a specific user on a specific item, for example, this entry, if we want to predict the value here, we perform the dot product between the vector of the target user and vector of the target item. So this dot product returns the prediction, the predicted rating for these two, for this user and item. So this dot product is kind of matching between the characteristics of the user and item. So in formulation, for learning these two matrices, P and Q, we minimize the squared error of the difference between the original metrics and our predicted metrics. So the goal here is to reconstruct the original metrics, the interaction data, the interaction metrics that we had, and we try to minimize the difference between our prediction and the actual rating in the interaction data. So in previous slide, we saw this prediction is a dot product between the two matrices, the representation of the items and the users, and then we also include a regularization term for avoiding the overfitting. By minimizing this objective function, we learn P and Q, which are the parameters for the representation of the users and items. Here is an example. We do not go through the optimization process. We assume that the optimization process is performed, and then we have the representation for the users and items. So for example, if we want to predict the relevance score for Bob on this movie, Green Book, then we do the dot product between the representation of this movie, the characteristics of this movie, and the characteristics or representation of this user. So this is the idea behind metric factorization. And in general, in collaborative filtering, we talked about neighborhood models, metric factorization, and these models, while working well, they also suffer certain limitations. First is the cold start problem. If the data is highly sparse, or if we have new users, new items, for users and items that we do not have any interaction, we do not have any data. This approach, collaborative filtering, both for the neighborhood models and factorization models, they fail to predict the rating, or maybe their accuracy would be a problem. And second problem is the popularity bias. I think you would have a presentation here in other sessions about the fairness and also bias in IR recommender system. Maybe you would see more about it, but popularity bias refers to the fact that certain items are interacted a lot. Those are popular items. Certain items are interacted less or maybe rarely interacted by the users. Those are maybe unpopular items. So the problem with the collaborative filtering is that because it's based on the interaction data, interaction from the users, these approaches, they tend to recommend popular items more. And the less popular items, unpopular items are usually ignored, which is the problem that those items would not get enough exposure from the system. So these are the limitations of collaborative filtering. Second category of the algorithms or maybe approaches in recommender system are content-based, that in this approach, instead of using the interaction data, we use the content information for the items to generate the recommendations. For example, if you have a user interested in fantasy novel, then content-based recommender would recommend same genre, same content, same category of the items to the user. So just to connect to the previous slide, to the limitations of collaborative filtering, if we have a user without just a new user and also a new item, this user rated, maybe interacted with this item, this is the only interaction we have. So these users and item, this user and this item are kind of isolated in the space of the interaction among other users, other items. You can see collaborative filtering would fail to generate recommendation for this user or maybe find similar items to this item, but content-based recommender would be able to find similar items because it only relies on the content similarity between this item and other items. Content is also, we assume, is available. So the process in content-based recommender, first we need to find a way to represent the content. It's in the form of maybe keywords, genre, maybe tags, or maybe textual information. We need to first represent the content, the items in the system. One way it can be like representing the item as a keyword vector. Keyword can be like the genre keyword, maybe tags, or maybe words in the text using TF-IDF, just term representation, the term frequency in the description, or maybe in the other metadata related to the item. Or it can be, you can use language models like BERT for learning the embeddings for the item. So given the textual information, the content information, you need to represent the item. The second task here is user profile. Given the representation for the items that you learned from the content information, you need to form the user profile. So based on the interaction, even one or two or even few interactions you have by the users, you can just take those interacted items, their embeddings, and aggregate them. By aggregating the representation of those interacted items, then you create the user profile. And the last task is recommending items. You have the representation for the items, representation for the users, and then computing a dot product would give you the relevance score for all unseen items. So here you can see an example. So assume that here we pre-computed the content representation. In this table, we have 7 items, and these are the features. Might be embedding or might be the term frequency that we created by TF-IDF. And here in last column, we have the interaction of the target user, user U. So the first item, user U liked. The third next item, the user did not interact yet. Maybe we need to compute the relevance score for those items. Item 5 is disliked. And last item is also like preferred by the user. Based on these interactions by the user, we take the representation of these three interacted items. Maybe, yeah, the item 5 needs to be, I mean, the representation should be multiplied by a negative value because it's like a dislike in this example. So by aggregating the representation of all these items, we create the representation for the user. So the aggregation can follow different operations. So here I think it's sum, but you can take the average or any other complicated operations. So given this aggregation user representation for the users and all other unseen items, so these are the second table here shows the unseen items and their representations, you can easily compute the similarity between the user vector, the user representation, and the and all other unseen items by computing the dot product between the, I mean, for example, this vector for item 2 and this vector for the profile of the user. The same also for item dot product between item I3, this vector, and this vector, and then you compute the similarity values. And based on the similarity values, if you want to recommend, for example, 2 items to the user, if you are working on top 2 recommendation tasks, then you can decide item I3 and item 3 and item 4 could be a candidate to be shown to the user. Yeah, go ahead.
For training the embeddings on cosine similarity?
Embeddings, I said, so embeddings here for the items can follow different approaches. You can, for example, take a language model like BERT to learn the embeddings. We didn't use the cosine similarity here, but here for computing the similarity value between the users and all other unseen items, we can take and compute it based on, I mean, using cosine similarity.
So you're going to fine tune the embedding model, or this will take off the shelf?
So it is again up. So this is not the main point. So maybe you can take very complicated language model. You can, for example, go for simple TF-IDF, I mean, term representation. Like you say, okay, genre is my feature. For each movie, all the genre, I just put the number for each genre as the representation for the item. This is the simple. Or you can say, I would like to take description of the movie, genre, tags, any other content information director, and then use them as input for a complicated language model to have a more accurate representation for the item. So here I said, so for example, 2 examples here I showed you. Yeah, you can go for a simple approach or maybe go for a complicated language models for the embedding. But the point here in this example is that we assume that we have these embeddings, these representation for the items, but it might be derived, I mean, from different process.
One question.
Yeah.
How important is actually predicting the user rating versus the rank? So let's say the universe of queries are there and our universe of documents are there. And I'm doing ANN, top 10, top 20. Doesn't really matter what the cosine similarity is as long as the ranking is more accurate. At least. So my question is exactly.
So is your question when we go for the rating prediction, when we go for ranking tasks, right?
Because the retrieval at K.
Yeah.
Retrieval at K.
Yeah. Yeah. So it's again, it's connected to the task that you're working on. These are 2 different tasks. We do not use the rating prediction task to retrieve relevant items. So the rating prediction task just predicts the rating. So in the old days, I remember certain systems we had that they showed, for example, to the user, not a ranked list, they showed the predicted rating. They said, okay, you just log into the system and then you would say you would see the predicted rating for a particular item. But Yeah, I agree. A ranking task maybe is more popular. So if it's a ranking task, the score, the rating, or the range for the predicted rating doesn't matter. Yeah, you just need to compute the score and just pick the, for example, K items with the highest score. Yeah. Sure.
Maybe I think I try to kind of why maybe they can ask the question that they colleague try to ask. So how can you guarantee that your similarity function has anything to do with the way you build vectors, right? So you say, okay, I'm aggregating some way, some kind of adding or you said some complicated way, and then you have your similarity. So you compute your ranking using similarity function, which from kind of what it looks like when kind of is constructed in a disconnected way from your aggregation function. So how can you guarantee that this aggregation and this similarity has anything to do
with the aggregation?
Yeah.
The fact is that these two processes are completely disconnected. They do not need to be connected. So you first compute the representation for the items, then you aggregate the interacted items, I mean, with certain process, just aggregate to come up with the representation for the users. And in the third step, you compute the similarity between the user representation and unseen items. So this similarity, computation step doesn't need to be connected to the aggregation process. So the aggregation is more like, for example, deriving the preferences of the users based on the interaction that user had in the past. If user interacted with 3 items, certain items like action movies, for example, the representation, the aggregation would also show this, that, for example, user is more interested to this particular type of the items. So it doesn't need to be connected. Is that clear? Yeah, so for the similarity function also you can, so here we said, for example, maybe cosine similarity, dot product, which is, the same as the cosine similarity, but you can also follow certain other, complicated process. But what matters, the point here is that you have to compute the similarity between these two vectors, but the process can be maybe based on your choice. So the advantages of content-based recommender system, we do not need to, collect the interaction data. We do not rely on the interaction from the users. We just use the content information. Also, these models are able to recommend to accurately predict the preferences of the, users with unique taste, like, for example, niche users interested in unpopular items that, for example, collaborative filtering would fail to capture the preferences of these users. And also this approach is able to recommend even unpopular items. It doesn't rely on the properties of the popularity information about the items. It only relies on the content-based content information. And the last one is that it's easier to explain the recommendations for this content-based recommender. We had the same advantage for the item-based, but here we also have maybe even more, the advantage here maybe is more clear here because we have the maybe term representation, certain features, certain explicit features about the items, their content information, and then we can easily understand why certain items are shown to the users. And the disadvantage for content-based is that it requires the information, content information. Sometimes it might not be available. Also, for certain movies, if you want to, for example, develop some algorithms to derive the content information for certain maybe domains, it would be challenging. And the most important weakness for this approach is that sometimes it recommends some obvious items to the user. So it is against the diversity of the recommendation. So if a user has, history of interaction, for example, with action movies, all the recommendations in the future would be action movies because it only follows the content information. It doesn't do the diversity. It doesn't generate the recommend diversified items to do the exploration in the space of the items for the users. So this was about the content-based recommender. Any other questions about this approach? Yes.
You mentioned cold start problem.
Yeah.
So in this case, obviously, you have a query and a document. The document, for the query itself, if it's a cold query, it's fine. You can do it based on this. But what if it's an unseen document?
The document doesn't have any interaction, you mean?
The document is not there. It's a new document.
New document. So you have the content for the document. You can compute the similarity between the content of this new document and all other document in the system, right?
Yes. But the problem here is not at the point of inference. So if the document will come in future, but at the time of prediction, there is no document at the universe of documents. So at the point of inference, when you're searching the space for the document is.
You mean the document doesn't exist in your catalog, but you want to recommend it?
For example, if I am, let's say, trying to get an item like iPhone 17, which is not there.
Okay.
It will come out in, let's say, 2 weeks.
Okay.
But I want to list it. And right now I'm going to fix fix my keyword and all that stuff. But the item is not there, but it will come in 2 weeks. So at that point of inference, there is.
Yeah. That might be a new problem. The easiest solution would be for a system designer to add this item to the system, to the catalog. So we assume, so in recommender system, we assume that we have a catalog, all the available items in the system, and then we find the relevant ones. Even in with this assumption, the task is challenging. If it goes to your task, then it would be even more challenging. So it doesn't work. Like this. If the item is not available in the system, yeah.
Why not we need to have to collect the user interaction data? Like, about the taste of the user, we need to know about his history.
Yeah.
So we need to collect the data.
Good question. Yeah. So here we did not say it's effective for new users. For new users, you're right. Again, we may not be able to recommend to the user in the content-based recommender, but we said it's effective for cold start problem for users with few interactions, 1 or 2. If you have, for example, 1 or 2 interactions, then this approach would work. We can recommend to the user. But yeah, you're right. If there is no interaction, that's different. So maybe we should go for certain other approaches. Yeah.
Giving a score to analyzing the content of users on certain items, and then give a score to the content, like a semantic analysis, and then analyze based on the content.
You mean content for the users, right? So here we only talked about the content about the items, but you're saying some demographic information about the users. Yeah. Yeah.
Like 4 stars and then being some comments.
Yeah.
You ever consider using those comments?
Yeah, that can be also an option, extra information included in the system. You can also, for example, when creating the user profile, you can take those information into account. Like for the user, you can also have other language models to just have certain other representation based on the comment on the items. Maybe you just combine, aggregate this user profile that you derived based on the interaction with the items, and also the embedding that you derive from the comments. some way you aggregate them. Yeah, those are extra information, but here the example I showed you is the basic information required for the operation of the content-based recommender, but you can go for more. Even we have also in the next slide, I have some example with other types of input and information for the hybrid recommender. You can also go for the connection between the users. Like for example, in a platform, while user interact with the items, we have also social connection between the users. So we have certain other recommendation approaches that you can incorporate those information also for the modeling part. Yeah. So the next one is hybrid recommender. So in the hybrid recommender, we try to combine the input or maybe the recommendation model or the output from different recommendation models to leverage the benefit from each recommendation approach. So far for the collaborative filtering, for the content-based recommender, you saw they have certain limitations and advantages. So by combining them, we try to leverage the advantages of all the recommendation approaches in order to just overcome the limitations of each. So here is an example with different recommendation, like input data from different sources. You can build a recommendation, not model, a component which may contain inside this box. We may have multiple recommendation approaches, all of them, maybe collaborative filtering, content-based, knowledge-based. And you just aggregate them to generate the recommendations or the relevance score for the items. There are three general hybrid recommender approaches. The first one is just training different recommendation models, taking their output and then aggregating their output or aggregating the representation for users and items that you learn from each model. The second one is bigger hybrid recommender model that inside you have multiple recommendation models that internally it takes the input and generate the and train the recommendation model inside this bigger component to generate the output. And the last one is like a sequence of the recommendation model. The output from one model would be the input for another model. So I have one example for the first one from this paper that I'm showing here. I thought it might be interesting for you. So the big architecture, the complicated architecture here, you do not need to understand it right now. But the point that I want to share here is that in this architecture, it's like a hybrid recommender model. It combines the collaborative model with the content-based model. So here we have the interaction data in the form of the graph. Then we have, graph attention model to learn the embedding for items and users. And then we also have textual information and maybe a language model like BERT is used to learn the embedding for users and items. And there are certain approaches for combining the embeddings for the items and embeddings for the users. Then after combining them, it results in one embedding for the users, one embedding for the items, and then the problem would be just computing the relevance score for the target items for target user. So this is an example of a recent research work that shows how two models can be combined for a hybrid recommender. So the next approach, recommendation approach, is context-aware recommendation. In context-aware recommendation, we utilize the contextual information about the contextual information for generating the recommendation. So it's known it might be able to generate more relevant recommendations to the users. Contextual information can be like time, location, purchasing purpose. For me, for example, I may like to listen a specific song in the morning, but the same song I may not like to listen in the afternoon. So it may depend, depend on my, types of the activity that I do in the morning, in the afternoon. So the context here is morning, afternoon. Or in the e-commerce, in the sequences of interaction and purchases that we make in Amazon, for example, I may be a user interested for certain category of the items, but inside I have one item completely different. That might be like not the purchase for myself, it might be a gift for someone else. So that is the context, purchasing purpose. By taking into account the contextual information, we can have more accurate recommendations for the users. So in general, here in this slide, I'm showing you the different context-aware recommendation approaches. As you can see, the context can be incorporated at different steps in the recommendation pipeline. In the data, after prediction for re-ranking, or maybe incorporated into the recommendation model itself. The first one, contextual pre-filtering, we only extract the relevant data related to the context. The example here, for example, if we want to, if a person wants to see a movie on Saturday or maybe in the weekend, then we only build the recommendation. Well, first we extract the data, input data for the weekend, and then we build the recommendation model on that sample of the data. So this is the contextual information that we build the model on the relevant data. In contextual post-filtering, we first generate the recommendations or maybe predict the relevance score for all the items. And then after that, so far it is the regular process in recommendation. Then before delivering the items, the recommendation to the users, we do a post-processing or re-ranking based on the contextual information. For example, if the context is watching a movie with family, and also we assume that the user is interested in watching movie comedy and drama with this context, like theater with the family, the same context, then after we generated the recommendation list, we remove all other irrelevant items like action movie for this specific context, if the context is watching movie with family, for example. So we do a post-processing in the generated recommendation list. And the last one is contextual modeling, even more challenging. The model needs to be designed to take into account different contextual information. So in the regular recommendation model, for example, in metric factorization, the objective function that you saw, it was two-dimensional. We had user items, and then we just trained the model to learn the representation for these two entities. But in the contextual information, if it's like a contextual modeling, this approach, we have to include more dimensions. We have to have more constraints in the training phase. So this is the original recommender system. We have two-dimensional problem, users and items, but in the contextual modeling, we have more dimensions. It may be tensor-based recommender system that besides the users items, we have times as well. So we can also have even more location or maybe purchasing purpose, even more dimensions for the model. So any question about this contextual recommender system? Yeah.
Is there a diminishing return on time?
Sorry?
Is there a diminishing return on time? So most recent context versus old context.
So that is maybe something relevant to maybe session-aware recommender system or sequential recommender. But here it's more about the context, like we do not take into account the order or maybe the time into account. The time here is used for the contextual information, like weekend or weekday, like maybe certain seasons. Yeah, it's not based on the sequence or maybe being the old interactions or new interaction, but the one that you're saying is related to other topics. Yeah. The next approach is calibrated recommendation. So calibrated recommendation, first, I would talk about the calibration as a kind of metric, how calibrated the recommendation is. So the calibration in recommender system means that how well the generated recommendation, the distribution of the the distribution of the item categories in the recommendation list follows the distribution of the item categories in the user profile. So example here, if we have a user based on the training set or the profile of the user, we observe if we have a user interested in 70% to action movies and 30% in drama, then calibration says the recommendation list should also follow the same ratio in the list. So the items should be from the same ratio of the categories. So it can be a measure of the recommendation quality, specifically in the sparse data. When you compute the accuracy metric like precision, recall, NDCG, the problem is that if the data is very sparse, the value computed for these metrics would be very low, which is not that reliable. But if you go for the calibration, at least in that situation, you can make sure that, for example, the category of the recommended items would be same as the preferences of the user in the input data. So here is the example. If we have a user with this interaction behavior, like 50% action, 30% drama, and 20% sci-fi, we create a distribution for this user this way. This would be the distribution of the item category in user profile. And for the recommendation list, we do also the same, assuming that we generated the recommendation list, the category for the recommended items followed this ratio. We have this distribution, and the difference, the distance between these two distributions results in the degree of miscalibration. So we can use different distance function here. I'm showing you the KL divergence, but you can go for certain other distance measure for the, distributions, just like Jensen-Shannon divergence, but there are many others. But the point here is that if we have lower distance between the two distributions, it means that our recommendation is highly calibrated. If we have more high distance between the two distributions, then we can say our recommendation model or the recommendation list we generated is not well calibrated. So this is the metric for computing the calibration. We can also think about calibrating the recommendation list. So you generate a recommendation list, like a long recommendation list. You have the input data, you build a recommendation model, you generate a longer recommendation list, and then you apply this calibrated recommendation algorithm, a re-ranker, or maybe a post-processing approach to generate the final recommendation list. So this final recommendation list, after processed by this algorithm, would be more calibrated. So the formulation for this calibrated recommendation follows this equation that it has two terms. It just tries to maximize this term. Like, for example, you have a relevance score for each item, and also you compute the KL divergence, or the distance between list created so far with the user preference in the training set. So P is your training set, Q is the distribution of the item category in the recommendation list generated so far. So you have empty list, and you just one by one add the items to the list. It's like a greedy approach that you just add items to the list one by one in order to maximize the relevance and the calibration of the generated recommendation. So lambda here plays the role, the trade-off between the relevance and the calibration. If you have higher lambda value, then you would have more calibrated recommendation. The focus would be more on the calibration. And if you have lower lambda, then lower calibration. So there are also certain improvements. So as also we had a question like when the user profile in the system is usually collected over a long period of time, and the user preferences usually evolve, that they have changes in their preferences. The items or maybe the types of the preference that we had, for example, years ago might be different from now. There are two research works that I'm sharing here. Maybe you may find it interesting that they try to improve the calibration measurement, or maybe calibrating the recommendation by taking into account the change in the user preference, not considering the whole profile of the user for creating the distribution of the user preference, but only considering the relevant portion of the user preference when performing the calibration task. The last approach that I want to share with you is the advanced in the item-based neighborhood model. I would share the research works in this line that they try to, one by one, they try to improve item-based neighborhood models. They try to address the limitations of this model. This is the basic formulation for item-based collaborative filtering that we saw in previous slides. Given the all interacted items in the user profile, in the user use profile, we just compute the sum of the similarity between this, the target item and all the interacted items in the user profile, and this would result in the relevance score. So it's simple. So everything like X here is known is our interaction data, but the problem is this similarity matrix. So deriving this similarity matrix is a problem. The first problem, as we discussed in previous slide, is that in certain cases, if the sparsity is high in the input data, the similarity computation would be inaccurate, or in some cases impossible. So in this example here, in this interaction data, you see these 4 items, we cannot compute the similarity values between these 4 items and all other items in the system. They are kind of isolated. There is no interaction, or maybe few interactions on these items, and we cannot find neighbors or similar items for these items. The second problem is that for creating the similarity matrix based on item-based neighborhood models, we have to compute the similarity value between each pair of the items. So of course, the similarity matrix is symmetry. We need to perform this computation for less than half of the size of the whole matrix. But again, it's a lot. It's computationally expensive. So here is an example. If we have 100,000 items in the system, then the similarity matrix requires around 5 billion computation. So to address this issue, sparse linear method is proposed. So the idea in a sparse linear method, or SLIM, is that instead of computing the similarity value between each pairs of the items, we can learn this similarity matrix. So the objective function for a SLIM follows this equation, that we try to minimize our prediction. XS is our prediction, our reconstruction of the interaction data. We just try to minimize the difference between the prediction, our reconstructed metrics, and the original metrics. And we have also certain other regularization terms and the constraint that, for example, diagonal should be 0 because we just want to avoid the self-recommendation. Each item has the similarity of 1 to itself, and if we do not capture this, then the item itself might be it might recommend itself. So to avoid self-recommendation, we have this constraint. Also, similarity value should be positive is another constraint. By minimizing this objective function, we will derive, similarity matrix S. And the question is why SLIM would be more effective than item-based neighborhood model. First, it requires less computation compared to the item-based neighborhood model. It does the optimization process with the objective function. And the second is that it just tries to capture the hidden patterns in the data. So in the item-based neighborhood model, we looked for the direct connection or overlapped item between two items to compute the similarity value. But here, because we're doing the optimization, we optimize the objective function, it would be able to capture some hidden patterns in the data, which might not be the case for item-based neighborhood model. So here is an example. If you have two items like A and C with no with no user to rate both, rating both, but we have another item that we know the similarity value between that item and each of these two items. Then maybe it's not the case for original item-based neighborhood model to compute the similarity value between A and C. But for SLIM, I'm not sure if it does, but it might be the case that during the optimization process, it captures these hidden patterns. So the cases that, for example, item-based neighborhood model fails to compute the similarity between two items, this one, SLIM might be effective. While SLIM is more efficient than item-based neighborhood model, but still the optimization process for this model requires a lot of computations because we have to do the optimization, go through all the interaction data in our input. To further improve the performance of SLIM algorithm, a lot of other research works are proposed for simplifying the objective function, for finding the closed form solution for solving the objective function. Instead of optimizing the objective function, doing iterative process over the interaction data, if you have a large interaction data, then you have to do a lot of computation for learning the parameters. So these are the work that I'm sharing with you. You might find interesting, but one of them, just to explain, the idea is simplifying the objective function, removing the L1 norm, and also the constraint that all the similarity values should be positive. Then it enables to compute or maybe derive the similarity matrix without doing the optimization. We can solve this equation in closed form. So the equation is here. The details of this derivation, you can look at the paper. But the point is that with this closed form solution, you do not need to optimize the objective function, which might be computationally expensive. But here, with certain mathematical notation, you can derive the similarity matrix. So we address these two challenges, limitations of the item-based neighborhood models. Still, the last piece of the limitation which leads these models to not be practical is the memory. Still, all of these models assume that the similarity matrix, item similarity matrix, which is huge, if we have 1 million items in the system, the memory needed to store this huge matrix would be 900 gigabytes. So this is, another challenge that might hinder the usage of this, the model in practice in the real world. To address this limitation, a low-rank neighborhood model is proposed. So the idea here is instead of learning the big similarity metrics, we can learn two low-dimensional variables, two low-dimensional matrices, U and V, such a way that U and V would reconstruct similarity matrix S. So the objective function is the same. The only difference is that we just replace. So this U also should be red, sorry. So this, the only difference is that we replaced S with U and V. So the dot product of the U and V would reconstruct similarity matrix S. In this case, instead of storing big similarity matrix in the memory, you can store two small matrices in the memory, which, I mean, back to the previous example, for storing these two variables, these two matrices in the memory, you can easily, you would require maybe 0.02 gigabyte instead of 900 gigabyte memory, which makes the model more efficient and also to be used, I mean, more practical. So this was the last approach I just wanted to share with you. I think we do not have much time for the, one small piece for the evaluation. I didn't focus on the evaluation because I know you have other talks and sessions about the evaluation in IR. So to avoid the overlap, I just skipped it. But maybe I can also skip this part, but the slides would be shared with you. And in conclusion, recommender system is an important ingredient of the commercial platform, the online businesses. So it has application in wide variety of domains. And in this presentation, we reviewed some important recommendation approaches. There are, I mean, some other approaches as well, but we try to just cover as much as possible. So in the last part of my presentation, I tried to show you a sequences of the research works that they try to improve a particular algorithm, the algorithm that was developed, I don't know, more than 20 years ago. You saw how the algorithm was improved. First, item-based neighborhood model, then slim to efficiently and effectively learning similarity metrics, and then, I mean, the algorithm is, for example, to make the similarity derivation more efficient, and then low rank neighborhood model. So you saw the sequence of the improvement in a particular algorithm, but still there are a lot of challenges and room for more improvements that we can work on. So here is the resources. There are many other resources like dataset and recommendation tools. So the first one, you here in these two links, you can find many interesting data sets for your research. And also the other ones, also for recommendation tools, these are the two that I used to use for my research, but there are many other ones that you will, you will be able to use for your research. So these are my references. Thank you for your attention. I'm happy to take more questions. Yeah.
Thanks for the talk. I'm curious, zooming out a bit. It seems like a lot of these methods are based on methods that have been around for quite a while. But like in popular culture, like with TikTok, for example, it seems like good recommender systems are extremely recent. Is there a fundamental underlying development that suddenly made these methods so popular, or is it also just engineering and?
You mean the choice of the models that I shared here, right? Yeah. Why? So here in this presentation, I did not focus on the popular ones. I just try to. If you see my slide, you will see it's not the recent model. So these are not the recent model, but I just try to share the approach with you. Maybe the last part was a bit more of the modeling, but I try to share the approach with you, like, for example, context-aware recommender system. There are many different algorithms that I did not explain here, or calibrated recommendation. It's like a concept that I try to share to give the idea to you. Maybe you find it interesting for your research, but the one that I showed in the last part, so that one was my goal was to show you the improvement that people, but there are certain other ones after this. I mean, the low rank neighborhood model that I showed you, that they also try to further improve, that I did not explain here, but you can find in the literature. So there is no specific reason, but my goal was more on the lecture side to just share the concepts.
Sorry, when are there state-of-the-art methods when the items are correlated in time? For example, obtaining one item after the other is important. I can imagine, for example, you want to offer a user wheels, but if he doesn't have a car yet, so it doesn't have any reason to offer a wheel for this user. So, for example, a mortgage that you want to offer him an insurance, so it doesn't make any sense to offer him an insurance if he doesn't have a house.
Yeah.
That.
Yeah, good question. So yeah, this is also another line of research. Maybe I think it's relevant to the next. Yeah, I'm not sure. Maybe next basket recommender, or I'm not sure. But I saw the papers in that line. People are actively working on. So yeah, taking to having certain constraints when you want to generate the recommendation. Yeah, if for example you do not have a phone, then the accessories might not make sense. Good question. I didn't cover here this specific line of research, but it relates to certain other topics in recommender system. So recommender system is broad, so maybe this is also another topic. You're right. Yeah. Any other questions? Yeah.
I saw that you did not cover XMC. That is also very popular.
What is that?
Extreme multi-level.
Extreme multi-level classification. I haven't got that.
Yeah, that's
Okay.
actually another software framework.
Or the tool, recommendation tool.
No, I mean, XMC is like a framework.
Okay.
I mean, it's also a very popular one.
Mhm.
Recommendation systems. I think there are people like Manik Verma from IT Delhi, and then Julian Ishkovic,
Mhm.
GNM.
Yeah, of course. So I had
Yeah.
certain concept conveyed to you. This is also the learning part for me. I can learn from it. I mean, take a look at it. Sure. Yeah, if any other questions, if not, we can have a break, right? Yes. Thank you.